Please, Nicolai Reshetikhin, quantum integrable system on integrable classical backgrounds. Here you are.
Okay, so it's a real pleasure and honor to talk at this memorial conference. I visited Vladimir in 1995, or was it 1994?
94.
94, yes, and I had the real pleasure to talk on sort of many times to Rodney at the time. Yeah, he's a remarkable scientist and very nice person. And yeah, I remember I started to read his book, I think when I was maybe third year student. So I was, needless to say, that I was very impressed. And the consequence of this reading, I think, is still visible today. So I'll be talking about hybrid quantum systems. So you can think of this system as the following. There is a classical phase space. Over this space, there is a bundle of algebras or vector bundle in the Schrödinger picture. So anyway, so this is classical, and this is quantum. And the dynamics, it's the usual classical Hamiltonian dynamics in the phase space. And then with the geometrical data that comes with these systems, this trajectory is lifted to the quantum evolution in the fibers. And this is really kind of the setup that's well known in physics as Born-Oppenheimer approximation, when atoms are moving according to the classical mechanics and electrons are in the field of these classical atoms, they are moving quantum mechanically. And there is no feedback from the quantum electrons to classical atoms. So in some sense, it's similar to control theory. So there is a classical dynamics on the classical phase space, and the parameters of the evolution of these parameters, it's controlling quantum system that lives on the top of this phase space. That's the idea. So this is why one can call them quantum systems on a classical background, but much shorter is to say hybrid quantum systems. So today I will explain how to, the definition, the setup for hybrid integrable systems. Basically, this is when you have a classical integrable system on the phase space, and then you lift it to something in the quantum fibers, which behave like a quantum integrable system. And we will see in examples how it looks like. So I'll mention the relation to deformation quantization, and we'll focus on one example. It's a spin Calogero-Moser system, and the corresponding hybrid system can be considered as dynamical Haldane-Shastry model. This dynamical Haldane-Shastry model becomes actually Haldane-Shastry model over the fixed point of the multi-time evolution of the corresponding classical integrable system, which is the Calogero-Moser-Sutherland, actually. Keep forgetting about him. System. Yes, so it's a joint work with Andrei Lashik and Ivan Sechin. Okay, so quantum systems on the classical background. So it's, as I already mentioned, Born-Oppenheimer approximation. So one can speculate that if quantum computers will ever be built, then it will be a quantum machine that will be controlled by the classical input. So of course it will be attached to some kind of usual electronic computer, and that would be another example of this hybrid system. So Peierls instability is another example. It was already mentioned in the previous talk. So the setup is the following. So suppose that we have a phase space of some classical system, which is a symplectic manifold. So typically it's locally it's dp/dq. We want to have a quantum system on the top of this classical system. Geometrically, it means that we want to have quantum algebra of observables sitting on the top of this classical phase space. So in mathematics, it's called a bundle of algebras. So locally, it's just you have the, say, if you have an open neighborhood here, then over this open neighborhood, it's this. And well, I don't want to repeat what a bundle of algebra is. So it's what it should be. So these algebras are quantum algebras of observables. So they are associative with the star involution, which is typically Hermitian involution of operators in the Hilbert space, and unital. So there is a unit and simple. So simple means, in the finite dimensional aesthetics, simple means that these are the endomorphisms, matrix algebras. So, but you see, what we want to do is we want to lift classical evolution to the fibers. So it means that we have to, so when we lift the evolution to the fibers, the tangent space to the system where the velocities are, well, we want to split it in the tangent space to the fibers and tangent space to the base. Such splitting is called a connection, and this is the same connection as usually sort of we have in physics, ddx plus a. It's just one way to think about it as the splitting of the tangent space. So then we can define the algebra of hybrid observables as sections of this bundle. So in other words, these are the mappings from M. So, well, these are sections locally. These are the mappings as X, which belongs to, to AX. And it's a section, so if you compose it with the projection, then it's the identity map. So sections, you can, just like functions, basically, you know, if you want to think about sections as functions, there is no big mistake. It's just, these are functions over neighborhoods. So as functions, they have pointwise multiplication. So then, so we want to have the pointwise star structure. And then if there is a center in this algebra of hybrid observables, this center is, sorry, not if, but there is a natural center, there is a natural center in this algebra. It's the functions on the phase space itself, complex valued functions. and they have Poisson bracket, so it's just the usual Poisson bracket, dz1 dp, dz2 dq, minus p and q. So the whole algebra of hybrid observables, these sections of our bundle, these are, so it's the module over the center. In other words, you can multiply functions on M, you can multiply sections by functions on M. It's an obvious property of every vector bundle. So then, once you have a connection, you can do more. You can define this bracket. Z is a function on M, S is any section. So it's the same Poisson bracket, but you don't use the derivatives, but you use the covariant derivatives for sections. And since you have a connection, you can use covariant derivatives. So this is just the covariant derivative with respect to the section. And obviously, because these are first order operators, and because here we have the commutator, it satisfies the property that it's acts by derivations. So it has this Leibniz rule. So now I came, you see, this is a mathematical talk. So I argued what should be the definition of a hybrid quantum system, and here is the definition. A hybrid quantum system is a bundle of algebras, for example, finite dimensional algebras, with a star structure and a Hermitian connection on this. And I should add here also, if we really want to have quantum mechanics, it's better be simple. In other words, if it's finite dimensional, the bundle is just a bundle of matrix algebras. So now, once we have such quantum algebra of observables, and in other words, this is the definition of the quantum, hybrid algebra of observables also. It's sections of this bundle is there. So then what are the representations of this hybrid algebra? Well, the representations of the usual associative algebra are vector spaces. Representations of hybrid algebra are vector bundles. So vector bundles such that every fiber is a module over the corresponding fiber of this hybrid bundle. So this representation should be Hermitian if we really want to be careful, and it should have a Hermitian connection, which should be compatible with our connection alpha. So we have two connections. We have two bundles. One is the algebra, the other is representation, and so we have two connections: alpha on the bundle of algebras and beta on the bundle of representations. And of course, they should satisfy this compatibility condition that if we covariantly differentiate the action of an element A of the algebra on the vector F of the representation, then we should have the Leibniz rule. So then it's the covariant derivative of A times F plus A acting on the covariant derivative of F. Okay, so now we have the hybrid algebra of observables, hybrid representations, and now what is the hybrid dynamics? Well, if we have a classical Hamiltonian, which is in the algebra of functions on M, which is the center of our hybrid algebra of observables, then we can lift the evolution of functions on M, the usual Hamiltonian evolution, to the evolution of sections of the hybrid algebra of observables. In other words, these sections now evolve according to the usual Hamiltonian dynamics, except now the Poisson bracket that we use, it's omega inverse ij di h0, and then the covariant derivative nabla alpha j of the section A. That's what the bracket is. So it's a natural lifting of the classical Hamiltonian dynamics to sections using the connection. But this is not the hybrid dynamics yet. But now, hybrid dynamics is when we add to the lifting of the classical dynamics, we lift a quantum twist. In other words, we have an extra section, which we call the quantum Hamiltonian in our hybrid system. And now the Heisenberg, now we have the evolution, which is hybrid between classical Hamiltonian dynamics and quantum Hamiltonian dynamics. This is the classical part, just the lifting of the classical dynamics generated by H0. And this is the quantum part, which is determined by the quantum Hamiltonian. So, okay, so that's the definition of dynamics. Now let's go to the integrable systems. So classical integrable system, well, we know quite well what this is. So it's a Lagrangian vibration of our phase space. Typically, yes, so algebraically it means that we have the algebra of classical observables, and in this algebra of classical observables, we have functions on the base as a Poisson commutative algebra, subalgebra. And we want to have rank n, so the rank of functions on n is 2n. In other words, the maximal number of independent functions in this algebra is 2n, and the maximal number of independent functions in this subalgebra is n. And if we choose this maximal set of independent Poisson commuting elements, this will be our Hamiltonians. And usually, say, if you look at the textbook, that will be the definition of an integrable system on a 2n dimensional phase space, that you have n independent functions which Poisson commute. So, I mean, in this geometrical setting, you can consider these functions as sort of coordinates on the base. Life can be more complicated. We can have 1 trillion of Poisson commuting functions and trillion minus 3 relations, and that they will define some very complicated surface in a 3-dimensional space, and still it's going to be an integrable system. So, okay. So now, when we have an integrable classical system, we have a multi-time dynamics. So for every Hamiltonian, we have the Hamiltonian dynamics, because the Poisson commute, it's a multi-time dynamics. It doesn't matter. So in other words, you can say that basically it's a flat connection. It means that if you have 2 points connected by the multi-time dynamics, it doesn't matter sort of in which path you go, as long as it goes along this multi-time evolution. So anyway, so this, I assume that this is obvious. So multi-time evolution of classical observables. So if you have a function on the phase space, then you can certainly, then that's the evolution. So now, hybrid integrable system. So now, so over the phase space, we have a vector bundle. This is our hybrid system. And then the integrable system is down below. We have a vibration over our M is fibered over B. In other words, there is a Lagrangian projection to this n-dimensional So this is 2n dimensional, this is n dimensional, and locally, if our system is finite dimensional, then this is like matrix algebra n by n. So locally. Okay. So now I think I may run out of time.
You still
How much time do I have?
12 minutes.
12 minutes. Okay. So yeah. Yeah. So yes. So just here's an observation. So suppose that we have a connection alpha and a flat connection on each pre-image of point B from the base. So point here and here is P inverse B. It's an for generic B, it's an n-dimensional submanifold in M. And so now we have alpha on E, and we have beta on the subbundle, on this bundle restricted to P inverse B. And so over each, well, these pre-images, these are Liouville tori. So in other words, over each Liouville torus, we have two connections, alpha and beta. And when you have two connections, the difference between two connections is globally defined one form. And then we can define quantum Hamiltonians if we have this one form in this particular way. And so then it's easy to check that these Hamiltonians satisfy this equation. F is the curvature of alpha, and as a corollary, we have a compatible system of the differential equations. And it almost goes in the opposite way. So if you have a system of compatible equations like this, then it's more or less equivalent up to something to the fact that you have these properties that I listed before. So this is the definition of the classical integrable, of the hybrid integrable system. Basically, it's the compatibility of these systems of differential equations. So there is more refined definition, which I don't want to focus on too much because for all practical reasons, that's enough. So now the relation, now you might say that this is all very artificial and it has nothing to do with anything. So it actually has relation to deformation quantization. Let me remind what the deformation quantization is. Suppose that you have an associative algebra. It has a central subalgebra. So, and suppose that you have a flat deformation family of this A0. So deformation family means that on A0 you can define a family of multiplications and flat means that this is the deformation of the multiplication on the same vector space A0. We don't change the vector space. And then, of course, functions are difficult to study, so algebraists like to do this. They like to have a formal version. Instead of functions, to have a to have formal power series, where we don't care about the radius of convergence. So, but whatever works. So I suppose that we have such family. So then, well-known facts. If you take the first coefficient in this multiplication, M1, take its skew-symmetric part, then it's a Poisson structure on the center, not on A0. That's a mistake. So then, if you will define, you can extend this from Z of A0 to the whole algebra. Then you will have the Poisson. Then the Poisson algebra, the central subalgebra of A0, acts by derivations on A. So we have this Leibniz rule. And then assume that we have an integrable system, this kind of on this deformation family. So that for each H, for each point in this family, for each associative multiplication, we have n independent elements in A0 such that they commute with respect to this star product. And also assume that these elements have the following structure. As H goes to 0, in other words, when we go back to A0, these Hamiltonians, they have the 0 coefficient, which is in the center of our algebra A0. And then we don't care about the first coefficients, they sit somewhere in this algebra. So then obviously the star commutativity of these Hamiltonians H in the first order gives the Poisson commutativity of classical Hamiltonians. And then remarkably, in the second order, it gives exactly the equation that we derived over here. This one. So again, I don't have enough time to explain why M2 has anything to do with connections and flat connections, but this bracket 2 is just skew-symmetric part of the second order in multiplications. So in other words, if we have a quantum integrable system, if in the semi-classical limit Hamiltonians behave in this way, then we have a hybrid system at the classical level. So I want to emphasize that usually in the deformation quantization, people consider deformation quantization of commutative algebras. So here we start with non-commutative. This is where the hybrid came from. Okay, here is an example. So we can, I will skip the origin of the quantum spin Calogero-Moser system. So there are several versions. The version that I'm talking about now, it goes back to Hikami and Wadati. And the first Hamiltonian is just sum of momentum. The second Hamiltonian is in interaction term has this permutation matrix that permutes spins. The third Hamiltonian, again, it has more complicated interaction and so on. It turns out that in the classical limit, these Hamiltonians, they have the form exactly as needed for a hybrid system. So H0 are the usual Calogero-Moser-Sutherland Hamiltonians. So this is the L operator Lux matrix, and these Hamiltonians are just traces of powers of the Lux matrix. And this hybrid Hamiltonians, they're a little bit more complicated, but if you really want, one can compute it. them in this system. So we have the classical multi-time evolution, the usual Calogero-Moser-Sutherland evolution. And on the generic n-dimensional level surface of these Hamiltonians, so that's the Liouville tori, full-dimensional Liouville tori. The multi-time evolution gives this flat connection again, and it gives hybrid evolution. So then we have a little theorem, which is the following. The well-known in physics literature freezing point, when q's are equidistributed over the circle and p's are zero, is the only fixed point of the multi-time evolution. There are no other fixed points. And corollary that over these fixed points, the Hamiltonians commute. And again, this is a known fact that at this point, the hybrid second Hamiltonian becomes the Haldane-Shastry Hamiltonian, and then higher hybrid Hamiltonians becomes this higher Hamiltonians for the Haldane-Shastry model for long-range spin interactions. In fact, this is a particular case of so-called low-dimensional Liouville tori or degenerate Liouville tori. So we just have a paper that's that was posted a few months ago with this combination of authors, but don't read it, please. A better version will be put in a few days, sort of more readable one. So the fixed point that we were talking about corresponds to the corner of this shifted principal Weyl chamber, but then there are one-dimensional Liouville tori, two-dimensional Liouville tori. This is for SS3. For SLN, there is a whole bunch of, so basically for SLN, it looks like this. You take the principal Liouville chamber, you shift it, and then walls of this Liouville chamber are kind of points where you have low dimensional Liouville tori. So then there are many interesting questions, and then going back to our occasion for today, when I was visiting Vladimir in 1994, we discussed a lot so-called Sine-Gordon system at the root of unity, and Rodney participated in this discussion in this very constructive but non kind of disrupting manner that he had. So actually, this is a very similar system. So I'll stop here, but I'll just say that the chiral pods model is in a similar way a fixed point of a hybrid evolution. And actually, this paper is the first example of of this hybrid integrable system. And just as in this case, so there is this fixed point over here, but then there are low-dimensional strata. And what are the analogs of these low-dimensional strata in the soliton cases, which is the case of the Sine-Gordon? These are the soliton solutions. If you think about the phase space of the Sine-Gordon equation, or any KdV, for example. So there's this complicated space where the variables are functions, but then there is a subspace with the discrete spectrum of the corresponding Schrödinger operator. These are the solitons. This discrete part of the spectrum, the solitons, these are precisely the analogs of the low-dimensional strata for finite dimensional integrable systems. And so in this case, so this is relatively well understood. the structure of the chiral postmodel. But what would be interesting is to study the hybrid dynamics, say, over one soliton solution for the discrete sign-Gordon space. But my time is over, so I want to thank the organizers again for letting me speak here. So consider this as the kind of advertisement of this subject. Thank you.